This is part 2, where we work example problems in which derivatives are applied in real-world situations. So let's get started. The force F acting on a body with mass m and velocity v is the rate of change of momentum. And again, try not to get too bogged down with the physics and the science behind these problems. Focus more on how calculus is being applied in a real-life situation, right outside of math. So F is equal to the rate of change of mv. If m is constant, then this becomes, you take the m out front and you have m dv dt, which is a. But like if you have something where the mass is changing constantly, like a rocket, right? It's expelling all that jet fuel, or like a rocket that's launching. It's expelling the jet fuel, so the mass is changing. The mass is a function of time, and the velocity is a function of time. But in the theory of relativity, the mass of a particle varies with v as follows. So yeah, the mass, in the theory of relativity, the mass varies, right? In the rocket example, the mass varies, but in a lot of situations, the mass is constant. So it's just m, you take the m out front, the mass doesn't change with time, and you have dv dt, a. But in the theory of relativity, the mass is equal to this constant here divided by the square root of 1 minus v squared over c squared. It's a function of the velocity. The mass is a function of the velocity, which is a function of time, so the mass is a function of time. Where m naught is the mass of the particle at rest, and c is the speed of light. Show that this is f. Okay, so to show that this is f, this is the most general form of the force on something. The most general, because, m is a function of t, v is a function of t. So what we need to do is, let's get mv for this situation. So v is just v, but m is this. So mv is equal to, we've got this 1 minus v squared over c squared, and then, right, that's mv. So now what we need to do is, to get the force, we need to say d dt mv, right? That's the force in the most general form, which is d dt So now what do we do? Can we take this derivative? Yeah. V is just a function of t. C is a constant, m naught is a constant. We use the chain rule, right? The derivative with respect to t of v, well, it's just dv dt. Well, we'll have to use the chain rule because we have to, we're going to be calculating this derivative as well, like v squared. That would be 2v dv dt. d dt of v squared is 2v dv dt. So we can absolutely take this derivative. So, right, we have to differentiate everything that's a function of t. Well, only the v is in this equation here. So how do we take this derivative? We use the quotient rule. We have a function of t at the top and a function of t at the bottom in the denominator. The v is the function of t. So, okay, quotient rule. Derivative of the top with respect to t is m naught. Now, dv dt is just acceleration, right? So m naught a, okay, times the bottom minus the derivative of the bottom. So what is the derivative of 1 minus v squared over c squared to the 1/2 power? That's 1/2 to the minus 1/2 times the derivative of what's on the inside. So 0 minus, so we have minus 2v, well, it's going to be, we'll have minus 1 over c squared, and then 2v dv dt, which is acceleration, right? 0 minus, and then the derivative of v squared over c squared with respect to t is 1 over c squared times 2v dv dt. Okay, so where are we here? We had the derivative of the top times the bottom minus the derivative of the bottom. Here's the derivative of the bottom times the top. All over the bottom squared. Okay. So we've got, and then so plus this minus and minus make this plus. These 2's cancel. We've got m naught v squared a over c squared times and then okay, now let's multiply by 1 in the form of square root of 1 minus v squared over c squared divided by square root of 1 minus v squared over c squared, and we get okay, but if you notice, if we distribute this here, we're going to get m naught a minus m naught a v squared over c squared, and then plus m naught a v squared over c squared. So this simplifies to just m naught a. And there you go. That's exactly what they have here. Right, we got 3 halves, 1 minus v squared over c squared to the 3 halves power, because this is this to the 1 half times this to the first. 1 plus 1 half is 3 halves. If in example 4, 1 molecule of the product C is formed from 1 molecule of the reactant A and 1 molecule of the reactant B, and the initial concentrations of A and B have common value, concentration of A equals concentration of B equals A moles per liter, then the concentration of C is given by this formula, where K is a constant. So what it's saying here, it's just it's just a simple A plus B gives C, right? This 1 molecule of the product C is formed from 1 molecule of the reactant A. We don't have like a coefficient of 2 here and 1 here and 3 here. It's all ones. Okay, the initial concentrations of A and B have common value A moles per liter. Then we have an equation for the concentration of C as a function of time. Right? A is not a function of time. K is not a function of time. So we have just these T's here. K is a constant. A, find the rate of reaction at time T. The rate of reaction, that's the change in concentration with respect to time. Do we have a differentiable function that we can work with? Yeah, we can plot this. This is differentiable. I mean, maybe there would be a value of t where you're dividing by 0, but in general, this is differentiable. So let's just set this up using the difference quotient just to give you that feel for how derivatives are applied generally for real situations. So the idea is, if we want to get a sense for the change in concentration with respect to time, then you've got delta concentration of C divided by delta T, right? This is the average change in concentration, like depending on the time interval you choose, right? Take the concentration at time t2, whatever that is, subtract that from the concentration at time t1, divide that by t2 minus t1. That's the average change in concentration over that time interval. But if you take the limit as delta t approaches 0 of the delta concentration divided by delta t, then that's going to be the derivative, right, of the concentration. Right? This is one of the definitions of the derivative. And this is the one that's most commonly used in real world situations. The difference quotient limit. Rate of change of one variable with respect to another. Now, can we do this? Can we find this limit? Yeah, as long as the concentration as a function of time is a differentiable function, we can absolutely do that, and it is. And you can get a sense of what this is telling you. It's the average change in concentration, but like with t shrunk down infinitesimally small, or delta t. So it's that rate at a point. So, okay, what is dc dt? We need to use the quotient rule. So let's come here. Why do we need to use the quotient rule? Because we've got a function of t in the numerator and a function of t in the denominator. And then k is a constant, a is not a function of t. So quotient rule, the derivative of the top, a squared k is a constant. Times the bottom. Minus. The derivative of the bottom is what? Times the top. All over the bottom squared. Okay, let's simplify this. Okay, these a cubed k squared t subtract out. So we've got that there we go. Part B. Show that if x is equal to the concentration of C, then dx dt is equal to k a minus x squared. Okay, so there's the derivative we just calculated. If x is equal to the concentration of C, well, okay, then we need to substitute C in here, or this in here, simplify, and we should get this. So let's do that. So dx dt is dc dt, since x is that c, and it's equal to this k, and then a minus, and x is c. So a kt plus 1 okay, so let's just simplify this. If we multiply this a by 1 in the form of akt plus 1 over akt plus 1, what do we get? We get, so it's going to be a squared kt plus a minus a squared kt, and then over a kt plus 1 squared, right? Because we made a common denominator and then combined the fractions. This is a squared kt, so a kt plus 1 all right. So this is k times, now if we distribute that squared, and then yeah, we've got a squared k over a kt plus 1 squared. There you go. So yeah. Part C. What happens to the concentration as t approaches infinity? To the concentration. Well, how do we evaluate this? Here's the concentration. We just say, what is the limit as t approaches infinity of the concentration? Now, this is an example of, when it comes to derivatives, you don't really, whenever you get into the real world, you don't really use limits as derivatives much. But you don't totally forget about limits. You can use limits for situations like this, right? If you have a function and you want to say, well, what's the limit of this function as it approaches infinity or negative infinity or some value, then limits are useful. It's a way of analyzing functions. Okay, so this is equal to the limit as t approaches infinity. And then also, what is this telling you? When we think about this concept, think about this conceptually. Well, it's just saying, when a long time has passed, where does it settle? Where does the concentration settle? Is it zero? Does it settle at zero? Does it settle at a finite number? Right? That makes intuitive sense. Just a really long time relative to like the normal time periods that reactions take. If we say a really long time has passed, where it's like, and a reaction usually would take 20 minutes to complete or 5 minutes, what happens if we come back the next day? That's kind of what this is saying. You see? So the reaction is, these types of reactions take 5 minutes to usually settle down and kind of start to come to completion. If we come back the next day, what's the concentration going to be? That's kind of how you can think about this. So the limit as t approaches infinity of a squared kt over a kt plus 1. Well, okay, how do we do this limit? Remember, for these, we want to, this is a rational expression. So with rational expressions, if you're taking the limit as t goes to plus or minus infinity, we're going to multiply by 1 in the form of 1 over t. We're going to divide the numerator and denominator by t. So we get a squared k over a k plus 1 over t. Now, we think about plugging in infinity. This goes to 0. So what does this limit go to? This goes to a squared k over a k. Interesting. The concentration of C approaches the initial concentrations of A and B. What happens to the rate of reaction as T approaches infinity? So there's the rate of reaction. What is the limit as T approaches infinity of d C dt? This is the limit as T approaches infinity of Well, as t approaches infinity, the denominator just goes to infinity, but the numerator isn't a function of t. This just stays as a squared k. So this limit is 0. And this makes sense because after a long time, the concentration is not going to be changing. It's going to approach a. What is the derivative? What is dc dt of just a? It's 0. Okay, and then what do the results of parts C and D mean in practical terms? We talked about that. Suppose that the cost in dollars for a company to produce X pairs of a new line of jeans is, and here's the cost function. Remember, we talked about how when it came to cost functions, in reality, there's no such thing as a fraction of a unit. So you can only increase by 1 unit or decrease by 1 unit, technically. But what they'll do is they'll create these curve fits of data and have like a polynomial expression for a cost function where like this is the not the overhead cost, or like this is one form of cost, and then like the terms multiplying by the higher order x is, you know, like labor cost or something like that. There's like methods for creating cost functions. So you get a nice differentiable curve here. Okay, find the marginal cost of the function. The marginal cost is just derivative of the cost function with respect to the units. So dc dx is, take this derivative, 3 plus 0.02x plus 0.0006x squared. Okay, part B. Find C prime 100 and explain its meaning. What does it predict? So, yeah, this is C prime. So, C prime 100, the marginal cost at the 100th unit. So, this is 3 plus 0.02 times 100 plus 0.0006 times 100 squared. So this is 3 plus 2 plus 100 squared. So we're going to have, this will be 1, 2, 3, 4 plus 6. So C prime 100 is equal to 11. Okay, what does this predict? What is this saying? C prime 100 is saying that if you wanted to produce one more unit, so you're producing 100 units, if you produced one more unit, your costs would go up by $11. That's what it's saying. Now, if we come to part C, it says compare C prime 100 with the cost of manufacturing the 101st pair of jeans. The point of this is that what is the technical at C 100 or at x is equal to 100? Well, what's the technical marginal cost? Like you take the cost function and you say C 101 minus C 100. Right? What is this telling you? Literally, if you produced 101 pairs of jeans, it would cost you this much. If you produced 100, it would cost you this much. Subtract the two. That's like the technical marginal cost. You know, there's no such thing as producing 0.2 pairs of jeans. The idea was, when we talked about this in the textbook, it doesn't make much sense to let, like, what we did here, we had, so delta C divided by delta X. We take the limit as delta X goes to 0. Well, delta X can't go to 0. Delta X can't be 0.1, 0.01, 0.0001. So, but the technical marginal cost is still this derivative. This is not the correct marginal cost at 100 jeans. This is. But what's going to happen, this is going to be approximately equal to C prime 100. We're going to get like 11.01 or something like that. So we can do this. We can say plus 3 times x plus 0.01 times x squared plus Okay, now we're going to store this as an equation. And now what we want to do is say that equation evaluated at x is equal to 101 minus evaluated at x is equal to 100. 11.1. You see, if this cost function were perfectly correct, and I guess you're kind of assuming that it is for the problem, then technically this is the marginal cost. Technically this is the cost to produce one more unit if you're at 100 units. But by definition, the marginal cost by definition is this derivative. So I hope that makes sense. It's just trying to illustrate how you go between like a derivative, a smooth curve, and like a real life situation. Because a lot of real life situations aren't necessarily smooth curves if you look at it by the most technically correct way of modeling it, but you can still model it with smooth curves. Like go look at the population example, the population function example. Whenever we went through the textbook, that explains kind of how you transition from a real world scenario that might not be technically truly differentiable to creating like a smooth curve that you can use to apply calculus. If P sub x is the total value of the production when there are X workers in a plant, then the average productivity of the workforce at the plant is equal to the total value of production with X workers divided by the number of workers. Part A, find A prime of X. What does the company want to hire? Why does the company want to hire more workers if A prime of X is greater than 0? So let's first find A prime of X. How do we do this? Well, we're just differentiating this with respect to X, right? This is A. This is A. And what do we have here? One function of X in the numerator and another function of X in the denominator. Let's use the quotient rule. Derivative of the first, just P prime of X. That's the rate of change of the value, the total value of production with respect to the number of workers, because the total value of production is a function of the number of workers, X. So P prime of X, the derivative of the top times the bottom. Well, let's just do this. Let's say we'll call this P prime. So P prime, the derivative of the top times the bottom, minus the derivative of the bottom is 1 times the top, all over the bottom squared. And we can, well, no, that's going to be it. Yeah, so that's dA dx. That's A prime. We can actually, let's put this X there. Okay. Why does the company want to hire more workers if A prime of X is greater than 0? Well, what is A prime of X? It's the average productivity. That's what they're trying to maximize, right? Because you might say, well, why don't we just maximize P? Because there's going to be a point where X is growing at a faster rate than P is growing as X grows. So this is going to start to decrease. The average productivity is going to start to decrease. So which would make A prime of X less than 0. If A prime of X is greater than 0, then that means that if for every small increase in X, A increases. They're trying to maximize A. So it wants to hire more workers. Okay? Part B. Show that A prime of X is greater than 0 if P prime of X is greater than the average productivity. Oh, and actually this is X squared. Sorry. Okay, so A prime of X is greater than 0. So let's take A prime of X, X, P prime minus P over X squared. So this is A prime. That's greater than 0. Now let's solve for P prime and see where that takes us. So this means that X, P prime minus P is greater than 0. So X, P prime is greater than P. So P prime is greater than P over X, and X can't be negative, so we don't have to worry about having to flip the inequality, dividing both sides by X. Well, yeah, and there you go. That's the average productivity, P over X. If A prime of X is greater than 0, then P prime of X is greater than the average productivity. In the study of ecosystems, predator-prey models are often used to study the interaction between species. Consider populations of tundra wolves given by W of T and caribou given by C of T in northern Canada. The interaction has been modeled by the equations. Okay. So the rate of change of caribou with respect to time and the rate of change of the tundra wolves with respect to time. What values of dc, dt, and dw, dt correspond to stable populations? So what would a stable population be? That would be when dc, dt, or dw, dt are equal to 0. The population is stable. It's not changing. So I guess, it can be unstable because it's declining too fast, or maybe it's just, kind of like rabbits or whatever can balloon too much. So let's solve for, let's set both of these equal to 0 and solve. So AC minus BCW is equal to 0. Well, no, that's not, they're just asking us, they don't want us to solve for anything. So yeah, that's it. dc dt is equal to 0 and dw dt are equal to 0. That means stable, but they don't want us to, they just want us to state the values of dc dt and dw dt. Okay. So yeah, so we've got part B. How would the statement, the caribou go extinct, be represented mathematically? The caribou go extinct. That would be that C of T is equal to 0. Not dc dt, because you could have dc dt equal to 0 and you've got 5 million caribou. It's just not changing. To go extinct means that there's no more caribou. So okay, part C. Suppose that A is equal to 0.5, B is equal to 0.001, C 0.05, D 0.001. Find all population pairs that lead to stable populations. According to this model, is it possible for the two species to live in balance, or will one or both species become extinct? Okay, so what we've got, we were setting these equal to 0. So we want to see with these values, let's see what the results for stable populations give us. This is the stable population case, right? So the idea is, can we have dc dt and dw dt be equal to 0, meaning that it's like perfectly in balance, but like at the same time w and c can't be 0. Neither w nor c can be 0 while dc dt and dw dt are equal to 0. You see? So okay, 0.05 times c minus 0.001 times cw is equal to 0. And then we have, for the wolf case, minus 0.05, or no, yeah, w plus 0.0001 cw is equal to 0. So we've got, if we divide, to get rid of these decimals, let's divide this entire equation by 0.001. So 0.05 divided by 0.001 is 50. So we've got 50C is equal to CW. Okay, and then here, let's divide 0.05 divided by 0.0001. 500. So 500W is equal to CW. So we can divide both sides by C. Let's see what happens there. So W is equal to 50. And if we divide both sides by W here, you get C is equal to 500. Yeah. So, I mean, if these were like unbelievably accurate models and like reliable over time, you know, just they're like these like fantastic models, then the idea is if you have 50 wolves and 500 caribou, that could stay in balance to where those numbers don't change and none go extinct, right? Because what we just solved for was that with these parameters, if dc dt and dw dt are equal to 0, then W is equal to 50 and C is equal to 500. It doesn't mean that no wolves are killing caribou and things aren't. It's like an equilibrium. There's not too many wolves to where they're eating all the caribou, but then there's not too many caribou to where no wolves die of hunger, right? Because you don't want, if you had so many caribou, then there would be an overpopulation of wolves. They would never go hungry. So it's like the perfect balance.